Hello everyone, I hope that you all are doing well. Let us discuss a very interesting question, and this question is from the complex analysis part and asked in the GATE 2025. Okay, what is this question is saying? In the question is given that omega is a non-empty open connected subset, means it is one type of a domain. Okay, and it is a f is a function from the domain omega to the complex number set, and it is a non-constant function. Okay, and in addition, f square is also is a mapping from the omega to c, and f cube is also mapping from omega to c. And these f square and f cube are not the composition function; they are defined in the pointwise sense. Okay, this and this. So do not confuse that this f square means f composition with f. This is not. This is wrong. This f square is a pointwise sense. Okay, and the statement S1 is saying what f is if f is continuous and f square is analytic, then we have to prove f is analytic. And in the statement S2 is saying that if f square and f cube are analytic, then we have to prove that f is analytic. But these are the not one line proof, means both these statements are true, but we have to prove one by one. So to prove this statement S1 has a very deep analysis. So in this video we will mainly prove the statement S1, because otherwise the video will be very lengthy. To avoid the lengthy video, we are providing the proof of the S1, and both of the statements are true. In this video we will prove that if f is continuous and f square is analytic, then we will prove that f is analytic. This is our target in this video. Okay, let us proceed. What is given that we are verifying the S1, means if f is continuous and f square is analytic, then we are claiming that f is analytic, and it is a true statement. Okay, for the time being, believe me, and I am proceeding to prove this one. Okay, let us prove it. Let me change the color. Okay, what is given in the question? Given that f is a non-constant, f is non-constant, f is continuous, and f square is analytic in omega. These three things are given, and omega is a non-empty open connected set. These things will be used because the non-empty and connected things mainly comes in topology part. Here in this question, interesting thing is that this question from the complex analysis part, but here we will use topology also. Topology. Without topology, this question cannot be proved. Okay, you will see later how topology is used in this question. Okay, our claim is that f is analytic in omega. First, means we have to check that for every point z0 belongs to omega, we have to show that f is analytic at z equal to z0. Okay, first we are taking a special case when f z0 is not non-zero. First we will prove for this case, then later we will prove that when f z0 equal to 0. So we are dividing in two cases. In the first cases we take f z0 equal to non-zero. In the second case we will take f z0 equal to 0. Okay, so given that f is a continuous function, what is given? F is continuous function. By using the continuity, this is a nice property of the continuous function, that we can find a neighborhood of at the point z equal to z0. We can find a neighborhood b z0 0 r. Neighborhood means it is a open ball with radius r at center at z0, such that f of z0 is non-zero. This is coming for all z from this open ball. Okay, and this fact is coming from the continuity of f. Okay, here the continuity f is used because in the given question f is continuous, so we can use this fact of the continuous function. If f is non-zero, f square z is also non-zero because it is defined in the pointwise sense. Therefore, f square z is non-zero on this ball, and it is also given that f square is analytic in omega, and b z not z0, it is a subset of omega. Okay, I have forgotten to write. Okay, this ball is the subset of omega. Therefore, f square is also analytic in b z 0 r. In this ball, f square is also analytic because f square is analytic in the whole domain, and b z not 0 z0 r is a subset of omega. Therefore, f square is also analytic on this ball. Now we will use a very standard result from the complex analysis. This result, what is it is saying? It is saying that if H is a mapping from simply connected plus open set G to C, and if H is analytic and H of Z is not equal to 0 for all Z belongs to capital G, then there exists an analytic function on G on capital G, so that G square equal to H square. Means one type of, we can find the square root of H. If H is an analytic function on G and it is non-zero, then we can find the square root, because G is nothing but the square root of H. Okay, means here the main thing is that G is analytic and H is equal to G square. Okay, we will use here because our f square is analytic and non-zero on this ball. On this ball we can use this fact. In the particular case, we take G is equal to this ball and our H is equal to f square. Okay, and our H is non-zero, therefore we can simply apply this result 1 in equation 1. Then what we will get? We can find a G function which is analytic on this ball. We are not claiming this is true on the whole domain omega, because these assumptions are true on this ball. Okay, therefore our result is true only on this ball, and this is sufficient for us. Okay, here the G is analytic. Here main thing is that G is analytic. And f square equal to G square. From this f square is equal to G square, by simple calculation we can derive this thing. Okay, and this implies that f of z is equal to gz or f of z is equal to minus gz for every z belongs to z naught b, z naught r. Okay, and from this we cannot draw any conclusion about the analyticity of f at z naught. Why? Because if f is equal to G on the whole ball, then we can say that our G, since G is analytic, then f is analytic. Or either in other hand, if f is equal to G on the whole ball, then also we can say this thing that since G is analytic, f is analytic. But there is a chance. What is the chance? That at some we can find some z1 and z2 in this ball, so that f of z1 is equal to gz1, but f of z2 is equal to minus of gz2. This can be happen. But if this will happen, then we cannot draw any conclusion, because in this case f is neither equal to G on the whole domain, or f is neither equal to minus G on the whole domain. Therefore we cannot say in the some part it is equal to G, in the some other part it is equal to minus G. F is equal to minus G. Therefore we cannot claim that f is also analytic, because we know that G is analytic and minus G is also analytic, but our f is not is neither equal to G or nor equal to minus G, because in some cases it is equal to G, in some other cases it is equal to minus G. Therefore we cannot claim that our f is analytic. But next we will claim that this possibility is not possible. Why? This is our claim. We will prove that either f of z is equal to gz for all the points in this ball, or f of z is equal to minus gz for all the points in on this ball. This is our target. If we will prove, then we will claim that since g is analytic and f is equal to g on this ball, therefore f is also analytic on this ball. Analytic on this balls means it is also analytic at the point z naught. Therefore we can prove that f is analytic at the point z naught. This was our main claim. How can we prove? To prove this thing, we will use the fact from the topology. Okay, we will define two sets. One set is defined in this way and other set is defined in this way. In the set A, we collect all the points from this ball where f of z is equal to gz. In the set on the set B, we collect all the points from the ball B where f of z is equal to minus of gz. It is clear that A and B are two closed sets. How? I am saying that it is clear, but you have to verify it. It can be verified easily because since f and g here all the discussions are going on the ball b z naught r. We are not discussing on omega. Here all the discussions are on this ball. Keep in mind. Okay, otherwise you will be confused. Our claim is that this set A and B are closed set. How these are closed set? Because our function f and g are analytic on this ball. Means f and g are both are also analytic, implies the continuity. F and g are continuous functions. Therefore their minus is also it is a continuous function, and the continuous function pull closed set to the closed set, and this set A can be written as f minus g inverse of 0 point, because f z is equal to, when f z is equal to g z, it implies f minus g z is equal to 0. Therefore z is nothing but the f minus g inverse of 0. Okay, therefore this set A can be written in this way. This set A is nothing but f minus g inverse of the 0 set, and we know that this is a closed set and this is a continuous function, so it pulls the closed set to closed set. This is a nice property of the continuous functions. Therefore A is closed, but this closed we are talking on the ball z naught b z naught r. So these sets are closed with respect to the subspace topology. Subspace topology means we are talking about the closed set C intersection with this ball. Okay, because all these points are coming from this ball. Okay, here the whole space x is equal to b, and therefore we are talking about the subspace topology. So keep in mind here all the discussions are on this ball and our universal set for this discussion is this ball is our universal set. Okay, and these things sets A and B are closed set with respect to the subspace topology x, and which is nothing but this ball. Okay, there, and in the similar way, since f plus g is also continuous function, and this set can be written in this way, and therefore this set B is also a closed set with respect to the subspace topology. I am emphasis on the subspace topology, because why? Because the students will be confused. Wow, because from this from the equation 2, it is clear that because we are collecting the point from the equation 2 is here because fz is either gz or fz is equal to minus z on the ball B. Okay, and we are splitting this ball on the two sets, and their union is equal with this ball. Here the students will confuse, because this is a closed set and this is a closed set. How the union of two closed set can be this open ball? It is an open set. But here the discussion is that this is a universal set X, so it can be both closed and open with respect to the subspace topology. Therefore I am giving emphasis on the subspace topology, otherwise students will be confused. Okay, so I hope that everything is clear up to this point. And b z naught 0 is equal to union of this thing. This is true because of equation 2, because from the equation to this one, either this is true or this is true for every points on this ball. Therefore our ball is the union of A union B. Okay, next we will claim that A intersection B is equal to phi. This is our claim. Why this is happening? Suppose there is a point X which lie on the intersection of A intersection B. Then it gives what? If it is lie on A, it gives f of x equal to g of x, and if it lies inside the ball inside the set B, it gives f of x equal to minus of gx. Okay. Then the transitivity property implies that f of x equal to minus of f of x, because g of x equal to minus of f of x and f of x is equal to g of x, it gives f of x equal to minus of x. So it gives the 2 f of x equal to 0 and implies f of x equal to 0. This is a contradiction to 1, because x is a point from the intersection and x is a point and this is a subset of the ball B z naught B z naught R. This is a subset. But on this ball, from the equation 1 is saying what? Equation 1 is saying that on this ball, this one f of z is non-zero. Okay, f of z is non-zero. But we are getting a point on this inside the ball which is equal to 0. So it is a contradiction. Therefore, it is not true. Therefore, there is no such x which lie on this intersection. Therefore, A intersection B is equal to phi. Now is interesting thing that now we will apply a result from the topology. This is a space. It is a connected set. Every ball is connected. It is a connected set. It is connected, and we are finding two closed set and their intersection is phi. Means it is a separation. But in the left hand side it is a connected set, but if the right hand side is happening and if A and B are both non-empty, then it gives a separation. But the topology is saying that this cannot be true. It will gives that either this set A is equal to phi or this set B is equal to phi. Here the topology is used. Okay, so we prove that A intersection B is phi, and it implies that either A is equal to phi or B equal to phi. Means our set is connected, this set is connected, and we are getting that connected set is equal to the union of two closed disjoint set, and this cannot be true. Therefore, either A is equal to phi or B is equal to phi. Therefore, either this f of z is equal to g of z for all the z belongs to in this ball, or f of z is equal to minus of g of z for all the points in this ball. And therefore we have proved our result. In either cases g is analytic, because either f is equal to g on this ball, either f is equal to minus g on this ball, and f and g are analytic. So therefore since g is analytic and minus g is analytic, therefore f is analytic on this ball. F is analytic on this ball, it implies that f is also analytic at z is equal to z naught, because this point z naught lies inside the ball. Therefore till now or up to this point we proved that f is analytic when f of z naught is equal to 0. Next, what is our task? We will prove that f is also analytic at every point where it is also 0, it is equal with 0. If once we will prove this, then we are done. Okay, since f of z naught is equal to 0, it implies f square z naught is equal to 0, since f square z naught is equal to nothing but f of z naught into f of z naught, and it is given that f square is also analytic and non-constant, and we know that the zeros of the non-constant analytic functions are isolated. Isolated means we can find a neighborhood of z naught where it is where f square has no 0 in this neighborhood except the point z0. Okay, therefore we can find a ball which I am taking, which is I am saying that neighborhood, we can find a ball b1 z0 r1 such that f square z is equal to 0 for all the points except the point z0 is non-zero. This is not zero, it is non-zero except all the points in this b1 ball, okay, with the radius r1. Therefore if f square z is not equal to 0, it implies f of z is also not equal to 0 because these are defined in the pointwise sense. And now by 3 and 4 it is clear that f is analytic on this ball except the in the previous result we have proved that if f of z is not equal to 0, then in these points it is our f is analytic by using our previous result, because f of z, if f of z is equal to not 0, then z is a analytic point. So therefore our f is analytic except the point z is equal to z0. But till now we are not saying that at the point z is equal to z0 f is not analytic. We are not claiming that because we do not know, it can be analytic or it cannot be analytic. Okay, therefore it implies that f is either analytic at z is equal to z0, and if it is not analytic, then it is a isolated singularity for f. Why it is isolated? Why it is not non-isolated? Because we have a ball b1 around this ball at every point our f is non-zero, and we have in the previous result we have proved that if f of z is non-zero, then f is analytic at that point. That means at the around every point inside this ball our f is analytic. So therefore our this point z0 can be isolated singularity. If it is a singular point, then it is a isolated singular point, because around its point, around on the every point it is analytic. So it is a isolated, it can be either isolated singularity or it is a analytic. If it is analytic, then we are done. But if it is not analytic, means if it is a isolated singularity, then we have to check how it can be analytic at the point z is equal to z0. Means if it is analytic, then we are done. So we are not considering this case. So therefore we are taking that z is equal to z0 is an isolated singularity. Because isolated singularity, why it is? I have told that around the every point on this ball it is analytic, therefore it is an isolated singularity. But isolated singularity has three possibilities. It can be either essential singularity, and essential singularity implies that from the Great-Picard's theorem says that Great-Picard's theorem. This is coming from the Great-Picard theorem. Great-Picard theorem says that if z is equal to z0 is an essential singularity, then every neighborhood, means if z not belongs to V, then f of V is dense in C. F of V is dense in C implies what? If f of V is dense in C, okay, therefore it is saying that f of V is dense in C, means it takes every point. If f z not belongs to this point V, then f of V is dense in C, means it implies that our this set f of V is a unbounded set for every open set containing this point z0. This implies that f is unbounded for on every open set containing z0. Okay, if f is a essential singularity. And the second possibility is that f can be a pole. If it is a pole, then it implies this thing: limit z tends to z0, f of z is equal to infinite. It also implies that f is unbounded near z is equal to z0. Okay, and third possibility is removable singularity. It implies that this limit exists and it is a finite quantity. L is a finite quantity. Okay. From these three possibility, we will discard this thing and this thing. This can be discarded by using the continuity of f. Since our f is continuous, then we can find a closed ball this b2 around the point z0 with radius r2, such that f of z is bounded, because the continuous function, it is a compact set. Okay, the continuous function takes compact set to compact set. Okay, and therefore the image of the set, the image of f over this set, this is bounded, because every compact set is bounded. It implies that it implies what? F is bounded on this ball, because f is bounded on its closure, therefore it is also bounded on this ball. Therefore we can find a neighborhood b2 of z0 on which f is bounded. But these two things, essential singularity and pole, are saying that it is unbounded near z is equal to z0. So these things cannot be possible. Therefore at most our z0 can be essential singularity. So up to this point we proved that our z is equal to z0 can at most be essential, can at most be a removable singularity. But this removable, and by the definition of the removable singularity, we know that this removable singularity can be removed by redefining it. Means if we are defining f tilde z is equal to f of z on this ball b z0 r0 r1, and it is defined in this limit form, it is equal to L. Okay, then this f tilde is analytic. F tilde is analytic. This because this is the definition of the removable singularity. Means removable means we can remove the singularity by making it analytic. Okay, therefore f tilde is analytic. But this limit is what? Since our f is continuous, this limit is nothing but f of z0. Therefore it is f of z is equal to this thing. It is I have forgotten to remove the point z0. Okay, here it is a difference of the z0. Okay, and at z is equal to z0, it is f of 0, and this is nothing but the definition of f of z on this ball. Therefore our f tilde and f are same on this ball. It is coming due to the continuity of f. Therefore since f tilde is analytic, and f tilde is analytic by it is coming from the definition of the removable singularity, and our f tilde is equal with the f on this ball. We are not talking about the whole space omega. Therefore f is analytic on this ball. Since f is analytic on this ball, therefore it is also analytic at this point z is equal to z0. So we proved this second case also. When f z0 is equal to 0, then also our f is analytic. From the fact 3 and 5, in the equation 3 we proved that our f is analytic at the point where it is non-zero, and at the equation 5 we proved that our function f is analytic at the point z is equal to z0, where f of z0 equal to 0. So we conclude that our f is analytic on the whole C. It is not C. I have incorrectly written because our domain is omega, on whole omega, this one. So we proved our result. I hope that you all understood it very well. Thank you all. I will see you again in the next time to verify to prove this statement S2, because video is getting lengthy. Therefore in the next video I will prove that this statement is also true. True means when f square is analytic and f cube is analytic, then f is also analytic. Okay, see you all next time very soon. Thank you all.